This will be a second lecture for chapter 6. On energy and power. So I'll do that. I'll do an example, a couple examples related to this. As far as that, and then the lab 6 is related to this concept. So again, we have our potential energy for gravity is mgh, mass times g, which is acceleration of gravity, h is the height. Potential energy of a spring is 1/2 kx squared, where k is a so-called spring constant. So for a spring, again, how much it takes to compress it, the force is k times x, where k is in units of newtons per meter and x is in meters, and force will be in newtons. And then x is how much you compress it. So it goes as a square of the compression because the force becomes greater and greater it takes to do that. All right? Unlike lifting a block, the force in lifting a block is constant. All right? It doesn't change. If it takes 10 newtons to lift it here, you're leaving 10 newtons the whole time. For a spring, on the other hand, the more you stretch it, the harder and harder it gets to do that. And likewise, compressing it, the more you compress it, the harder and harder it gets to do that. So I'm going to do an example here relating this, and also, again, kinetic energy is 1/2 mv squared, where m is the mass and v is the speed squared. All right, so let's do an example here, and this is in the book. Figure 623, and what we have here is a case of, we're going to have a compressed spring, okay, and we're going to put a mass on it. Let's say a mass of 100 grams, and K has a spring constant of, let's say, 100 newtons per meter, right? Okay. And we're going to compress it from where it is a distance of 10, let's make it 20 centimeters, all right? So we take a spring, put a block on it, compress it 20 centimeters so that we store potential energy in that. In this case, we then let that go, and what's going to happen? And we can actually do a demonstration of this, of case. So I'm going to follow the same thing out here. I'm going to do this as an example. This is approximately 10 centimeters. This ball probably weighs, instead of 20, I'll do 10 centimeters. This ball probably weighs, less ounce, so maybe it's 20 grams. And I don't know what this is for here, so I'm going to compress it okay. You see, when I let go, it comes back, converts that potential energy is released, which then gives a kinetic energy, and it rises a certain height. So that's what we're going to look at here, is when it uncompresses, the ball is going to go up a certain height. So what we have here is potential energy given by the spring 1/2 kx squared, which then converts to kinetic energy, 1/2 mv squared, and that kinetic energy turns into potential energy, mgh. So all three are connected. So we're going to figure out how high does this actually go. All right? So I'll do this one step at a time. So again, mass will be 0.02 kilograms. K is 100 newtons per meter. X is 0.1 meters. And that should be enough information for us to solve the problem. So let's look at this then. Okay. So first thing, potential energy of the spring, which converts to kinetic energy, which converts to potential energy. So PE of 1/2 kx squared will be 1/2 times 100 times 0.1 squared. Well, that's 100, that's 0.1. That'll be equal to 0.5 joules. So that's how much energy we have into this. All right. That then, so that's potential energy, which when it let it go, then converts it to kinetic. So we have 0.5 joules is kinetic, then converted to kinetic, which is 1/2 mv squared. All right. So we can find out how fast it's actually going at this point. All right, when it's actually first released. So that would be 0.5 is, so 1/2 equals 1/2 times 0.02 times v squared. So that those cancel out. That's 1/50, so that would be 50 equals v squared. So v would be approximately 7.1 meters per second, which may be about right. All right. So that's kinetic, so that's how fast it's going. Now we don't actually need this step to find out how high it actually will go. Because what's happening here is each one, this is 0.5 joules. The kinetic energy of 1/2 mv squared is 0.5 joules. And then how high up it goes is based on 0.5 joules. So we can just use each one, you got potential converted to kinetic, kinetic converted back to potential. So the final potential energy of 0.5 is mgh. And in this case, I'm going to use G is 10 meters per second squared. And in that case, this becomes 1/2 equals 1/50, 0.02 times 10 times h. So that would be, let's see, that's 1/5, multiply both sides by 5. So that means that h is 2.5 meters. Which isn't bad. I mean, the thing actually went up to about here, I think. So if this, but it's kind of hard to keep on track. But that's how high this ball actually was 20 grams, which I'm not sure how heavy it really is. That's how high this would go. So this would be a spring constant of 100 newtons per meter. Compress it by 10 centimeters, let it go. And this includes all the aspects of potential and kinetic energy. Again, keep it in mind that the total energy, I'm running out of room here, in this case, is conserved kinetic plus potential. So we have, this is all potential, so it's 0, then it becomes all kinetic, then it becomes all potential again, and all along the way it's 0.5 joules. So that's the example of potential and kinetic energy for a spring. All right, that is that part. I will now finish up chapter 6. I'll leave this up for a minute. So again, the height was 2.5 meters. It's kind of hard to see that exactly as far as that's the case. All right, here's the important expressions, and I will go on from there. So I'm going to do the last part here is on power, on chapter 6. And go from there. Okay, so power. Power is defined as work over time. So work is how much energy you take to do it. The power is how fast you actually do it. So this is joules. This is in units of seconds. This unit is a watt, named after James Watt, or capital W. So watts are power, units of power. The 100-watt light bulb, that's how much power it uses, but that's electrical power. So, example here related to this. Before I get into that, units of power, we have power. The English unit of power is the horsepower, which is equal to 746 watts. And this was actually defined, this was done by James Watt. What he actually did was looked up how much could a horse with a pulley not much of a horse pull in 1 second, 1 foot in 1 second. So in 1 second, this horse could lift up 550 pounds, 1 foot in 1 second. So 1 foot, 1 second, 550 pounds, and that's equivalent to 746 watts. So that's the unit of horsepower, and that's where it came from. I should get rid of, I got this backwards. So that's horsepower, right? Originally came from how much power a horse could generate. All right, now we use watts. All right, so another example of this, and we got other things, is if you climb the stairs, or if you lift, you climb the stairs, let's say you climb 10 flights, well, let's make it 10 meters, which is about 3 flights, 30 feet or so, 10 meters. You weigh a mass of 100 kilograms, right? 10 meters. How much energy does it take to climb that 3 flights of stairs? So 10 meters. All right, potential energy, or the energy it takes, is mgh, which would be 100 times 10 times 10, which would be 10,000 joules. All right, 10,000 joules to lift itself up 3 flights of stairs about 10 meters. Okay. Now, the way this works is if you go slow, it still takes the same amount of energy as if you go up very fast. What's different in the second case, if you go very fast, is you are generating more power, so it's taking you less time to get up to the top. This is the same thing as, say, runners. 2 people run a 10K, one does it in an hour, and the other does it in 30 minutes. They both weigh the same. The amount of energy it takes is the same in both cases. It doesn't matter how fast you run it, it's how far you run it. So, so you're both running the same distance. The thing is, the faster runner is generating more power. So they're generating more power. In this case, twice as fast, because twice as much power, because they're doing the same amount of work, but in half the time. So, let's say you do it very slowly, and it takes you 10 seconds for each flight, so the time is 30 seconds, which may be on the quick side. All right. Now, if you do it really quick, so you do each one in 2 seconds, that would be 6 seconds. So T1, T2, 6 seconds. All right. What would be the difference in power? Power is work over time. So in the first case, the power would be 10,000 joules over 30 seconds, which would be approximately 330 watts, which is actually pretty darn fast, pretty darn good. That's a lot of power to generate, but we'll just pick this example. If you do it in 6 seconds, it's pretty hard, trying to climb 10 meters in 6 seconds. That would be 10,000 over 6, which would be 1,600 and, let's see, 30 joules, 1,640 joules, 1,650 watts. That's a huge amount of power. So in both cases, you're using 10,000 joules, but in the second case, you're doing it 1/5 of the time, so you're gonna have 1 to 5 times the power in this case. So that is power, which is section 610 in the text, and that is the end of this chapter. All right, so that's chapter 6. We'll move on to chapter 7 next after this, which will be on momentums and collisions, and we'll be dealing with lab 7 will be related to that. That lab's already posted. So, all right, have a good day.